by Leo that prompted by Mo, we'll have a photo in this coffee break. That's going to be organized kindly by Emil. Thank you, Emil. He'll lead us to wherever we need to be. Yes, 2 more lectures, lunch, brief discussion on the fun we had yesterday, and then we are free for the weekend. Almost there. Super.
All right. Can you all hear me, or is this still not on? It's not on. Oh, Can you hear me now? It's on. Okay. Good morning, everyone. Everyone looks really tired. So I'm gonna kind of try to keep this like a little bit more fun, relaxed, maybe a little interactive. I guess we're gonna switch topics a little bit from talking about sort of differential geometry from like all of this like fancy calculus point of view, and we'll think a little bit more combinatorially. So today we're going to be kind of doing a lot of counting. So hopefully y'all are on board with that. So yesterday I talked a little bit about how Gaussian curvature can be described on like discrete surfaces. So we looked particularly at sort of a hexagonal crystal and sort of looked at what happens when we change the orientation, but we can generalize this to like any arbitrary mesh. So if you're, doing a 3D animation and you have your Stanford bunny or your Utah teapot or whatever, you can define curvature on that. And basically we do that by taking 2 pi minus the sum of the angles around a vertex. So this tells us a lot sort of locally about the sort of intrinsic curvature of a combinatorial mesh. Here, these do have geometry, so it's not strictly combinatorial. We do have the actual geometry of these structures. So I'm gonna do a sort of walk through one version of a sort of proof of how you can learn something about topology by looking at these sort of discrete combinatorics. So if we're looking at a particular vertex here, we can look at the total angular deficit. So that's just what I described before. That's 2 pi minus the sum of the angles per vertex. Likewise, I can define the total angular deficit for my surface by saying, okay, I've got 2 pi times the number of vertices minus the sum of all angles in my structure. So I'm going to do this calculation now a second way. Here, I'm going to not look at vertices, but I'm going to look strictly at these faces themselves. So if I want to figure out the angular deficit for face, so this is just like the polygon formula we probably learned in, I don't know, 8th grade in the US and probably kindergarten in Europe, because you all are like way ahead of us in the US. So here it's pi times the number of sides per face minus 2 pi is the total angular deficit for a polygon. Again, I can extend that to the entire structure here. So then I have pi times the total number of sides minus 2 pi times here the total number of faces. So I'm just sort of multiplying those through. Okay, so now this is the total angular deficit defined in one way. Here's my total angular deficit defined in another way. So now we can set these two equal to each other. And so here I'm going to say that, one thing. So I said this is pi times the total number of sides. And if I'm looking at one of these polygons, I have 3 sides here. But if I look at the other one over here, I have the same side as being double counted. So the number of sides is twice the number of edges in my surface. So now when I equate these things, I end up with twice the total number of vertices minus, I'm going to say 2 pi times some number is equal to here, over here, 2 pi times the total number of edges minus the number of faces. And so this, I can rearrange this to say that the number of vertices minus the number of edges plus the number of faces is some number chi. And chi is what is called the Euler characteristic. This is basically telling us about the genus of the surface. So I can show you sort of a different proof if you, it's a little bit longer, but basically you can take any arbitrary space graph and start removing dangling edges and try to reduce things to triangles, and you can get, like, you reduce things down to one triangle and you can get the same result. So this is one way of sort of taking this like combinatorial information and getting topology out of it. We can also do this again using the normal map that we defined yesterday. So here I've got a normal vector on my surface, and I'm tracing out some path on my on the unit sphere. And so I can also basically integrate the Gaussian curvature. So the Gaussian curvature over the total area is 4 pi times, again, this this number chi. And so what this is actually telling us is the number of times the normal gets wrapped completely around the surface. So we're just counting the number of times the number of coverings of this map. And so that's why this is sort of a topological invariant. So there's, I guess, a sort of geometrization theorem that says, okay, so we have these 3 curvatures. These are all sort of defined on our, kind of defined by our Gaussian curvature. And you can sort of map uniform structures onto them. Oh, I should mention, let me connect the Euler characteristic to genus. So the Euler characteristic is 2 minus twice the genus. So an Euler characteristic of 2 is something that has no holes. This has 1 hole, so it's 2 minus 2 times 1 hole is 0. So this is what our Euler characteristic is, and our Gaussian curvature, like, this is a flat surface overall. And for more than 2 holes, I'm subtracting 2 times the extra number of holes, so that's always going to be negative. So this is sort of another way of sort of counting the global Gaussian curvature in a surface based on its topology. And so there's sort of this idea of geometrization. So you can take surfaces that have either positive curvature or 0 curvature or negative curvature and sort of assign a uniform metric to them. And those sort of uniform structures here, these are all, I guess, works by C. Escher. So you have, for spherical space, you've got a sphere. For flat space, you have a plane. And so a torus, as you know, physicists all know, toruses are flat because we just draw periodic boundary conditions on either side and call it a day. And then this is the hyperbolic plane. So this is something that has negative curvature everywhere. So this is sort of a way of sort of coming up with like the most sort of canonical version of all of these structures. Okay, so I'm going to be telling you a little bit more about, so that's sort of a prelude. The rest of what I'm going to be telling you about today is something called orbifolds. And so that's a pretty fancy name. And a lot of what I'm going to be telling you comes from this book called The Symmetries of Things. This is by Heidi Burgid, John Conway, and Chaim Goodman Strauss. You might notice if you can read it that their names are not in alphabetical order here because Conway insisted on his name being first. But I will defer to the standard mathematical tradition of putting everyone's name in alphabetical order. So basically, we're going to be sort of talking about symmetries and their relationship to curvature. So the idea is we can define symmetries as translations or sort of motions of an object that leaves it looking the same. So that's not the most mathematical definition strictly, but I think that's good enough for us to kind of understand them. So we're going to sort of go through some like fairly more sort of simple, straightforward things first, and then we'll start getting into a little bit more of a complicated structure and sort of build up from there. So, okay, so here's a bunch of different flags. I keep forgetting there's like a copy of, I think, like Albania that's behind Switzerland. So Switzerland's supposed to be a square. So so I was just using it to like align everything. So my bad about that one. So here's a bunch of flags from around the world. And so for all of these, I'm gonna say ignore the boundary shape of the flag itself, and just assume that that fills the plane infinitely. So all of these share some sets of symmetry. So what do you all see? What symmetries do you see? So Vietnam would have a 2 pi on 5 rotational symmetry. That's one symmetry. Does Albania have that symmetry as well? No. Yeah, so there's a mirror at the center. Do you think there's other ways of expressing I don't know, Vietnam using like other symmetries? There's obviously a translational symmetry here, or sorry, a rotational symmetry here. I mean, we can say the same thing about Macedonia and Switzerland. Do we see any other symmetries about Vietnam? Yes. Yeah, so there's a mirror symmetry here. Any other mirror symmetries? I'm seeing some, yes.
Along each point of the star?
Yeah, so there's a mirror symmetry along each point of the star here. So I guess, what about Tennessee? So there's again rotational symmetry. Yes. Yeah, so there is a threefold rotational symmetry. Again, we're just assuming that the whole infinite plane is red, so you don't have to worry about the shape of it. Anything else? Yeah, so there's actually mirrors in this too, and they're actually at kind of funny angles here, which is why it's hard to spot. So all of these, well, most of them also have some amount of rotational symmetry. Albania and Georgia don't have a rotational symmetry, but all of these 6 share mirror symmetries. So all of these have mirrors in common. And so we can sort of define what we'd call like a fundamental domain as sort of the smallest unit here that's needed to define the entire object. So the fundamental domains I have for these particular flags are here. And so here they're all labeled by the number of mirrors that intersect at a point. So Georgia has 2 mirrors that intersect at a point. Tennessee has 3 mirrors, Switzerland 4, Vietnam 5, and Macedonia has 8 mirrors that all intersect at a point. So we're gonna be sort of defining those. And so what I basically do for these mirrors is I take my little wedge and I mirror it back and forth about each point, and that's enough to completely define the object in the plane. So here's a, yes. So that's a great question. So the flag of Japan, so these are all what we'd call discrete symmetries. The flag of Japan, I would say, has a continuous symmetry. So a rotation by any angle would be a symmetry of that. And so we're going to classify those slightly differently, but you can definitely understand symmetries using sort of like a continuous slide as well as like a discrete motion. So here I'm going to show you how this works on a 2D plane. So let's have a look and see. So what symmetries? So these are again mirrors. So what I guess what mirrors do you see? Where do you see them intersecting? Yes.
Four mirrors, the vertical, horizontal, and now it's like a square region.
Uh-huh.
There's, I guess, also four.
So there's I guess there would be four mirrors. So if this is like one of my square regions, so you're saying, sorry, vertical, horizontal, and the diagonal. So those are four mirrors. So there's, so yeah, that's one set of mirrors. And you're saying a rotation? Where fourfold rotation about where? About, oh, okay, yeah. So oftentimes mirrors, so okay, so let me go back and make one point about the fundamental domain. That's a really good point. So oftentimes we do have symmetries that are sort of shared by an object. So we were talking first about Vietnam. And so the first thing that people noticed was a rotational symmetry. And it absolutely has a rotational symmetry. So that would be taking this whole region here and rotating it by 2 pi on 5 over here. And so that is absolutely a symmetry. But the specific thing about these sort of fundamental domains is they're defined as the smallest region. So oftentimes, like a rotation will actually be like a larger like space. So the fundamental domain can actually be split up again by even a smaller symmetry. So we're just going to be looking at what's called these smallest symmetries. So it's not to say that those other symmetries aren't there. It's just we're specifically looking at a different subset of them. Yes.
Broken down into reflections?
No. So we'll see some places. We'll do one 2D example, and then we'll look at rotations that can't be broken down into reflections next. So it's often the case that you will see like the first symmetry we see, like we might be trained to look particularly for like rotations or translations or whatever, just based on like how we, grew up or whatever. And so we'll see those first, but if we looked at the smallest unit cell of that, maybe it can be divided or maybe it can't. Okay, so we had, I guess, 4 mirrors through each of these cells. Do we see anything else? Do we see any other places where we have reflection symmetry? Yes. Yeah, so we have reflection symmetry through the lines like this. Any others? The diagonal? Is that what you said? Yeah. So also we have reflection symmetries through these diagonals here. We've got one place that we have 4 mirrors here. One place we have 4 mirrors here. Anything else? Does anyone see anything else? putting the brown things like here. Oh, from a center of a square. This way? So it would be for this small object, but like, let's trace it out here and I get to like along this point, and so that's a little bit harder to see. So I'll say you have caught all of the mirrors. So let's draw them out. Let's see if I have, oops, hold on. This is where they are for, oh, sorry. Okay, so what we have, let me draw on the screen and then I'll erase it. Okay, so we've got mirrors that go through here. And then mirrors that go through here. And then, so we've got a four-fold intersection here, a four-fold intersection here, and then the one thing is that there's this other point right here where we have two of the mirrors from those four-fold ones intersecting. So I'm going to say that there's, so the symbol for mirror is a star. So I'm going to say this is a star 4, star 4, and star 2. So that's how I'm going to define this. Let's see if I can, no, I think I have to go erase it. Otherwise, these are going to be on for the rest of the slide. Okay. So how does this work for an orbifold? So we've got our fundamental domain is like 1 4-fold symmetry here, 1 2-fold symmetry here, 1 4-fold symmetry here. So we've got just this little triangle here, and that's all we need to express the entirety of the plane. So let's, this is a video from software that's called Attractor. And yes, it is spelled that way. It's a Portuguese group that came up with it. Basically, we have our domain that has mirrors, and then every time you see it, it kind of like stamps down a different bit of the pattern. And so from this, you can basically unfold the little triangle, and that'll lift all the way up to the plane. So you were asking about rotation. So let's have a look at some rotations next. So yes.
It's like interesting literature on like tiling a plane with geometric shapes and like or set of shapes that can tile a plane. But given a pattern on a plane, there is understood like how these two things relate.
So are you talking about like sort of quasi-crystalline things or like aperiodic tilings or like, okay, so I guess there's recently been a thing on this thing called the hat tile. And so the hat tile, you may have heard about it. It got a lot of press. So the hat tile is something, it's a shape, or it's actually a 1 parameter family of shapes that goes from the hat on one parameter all the way to what's called the specter at the other parameter. And so these are things that tile the plane asymmetrically. So there is no fundamental domain. There is no smallest region that can capture that tiling. So that's really, that makes it actually really hard to study. So it was actually quite impressive that they were able to, actually it was a recreational mathematician who first came up with the structure and then contacted some people in, so Chaim Goodman Strauss was one of the people, and oh, what's his name? Oh, I have this thing where if I picture someone's face, I instantly forget their name. So if I remember his name, I'll shout him out. Craig Kaplan. Craig Kaplan was another person. So they were able to sort of take the structure, these shapes that the sort of recreational mathematician found, and were able to work all three of them together to create the sort of theory of this. That's a great question. So those are actually something that doesn't get categorized by this sort of notion. Yeah, so here I think to see rotational symmetries, you have to ignore the coloring on Maryland, the coloring on South Korea, and the little dashes in the lines of South Korea. But I think everything else works. So these, I guess, these all have rotation. So what rotational symmetries do you see? Yeah, so there's, which ones? Yeah, Maryland has a twofold rotation. Yeah, so a rotation by pi about here. Excellent. Anything else people see? Isles of Man, yeah. Yeah, so there's yeah, 2 pi on 3. Yeah, rotation about, I guess, their crotch. I don't know, whatever the center of that is. I mean, the Isle of Man is a pretty funny flag. Anything else?
Tornado, if you ignore the length of the thing, 90 versus 180.
Yeah. So NATO has either a 90 or 180, depending on if we are keeping track of these lengths or not. Excellent. Yeah, 2 pi by 5 for Hong Kong. Hong Kong, I really like their flag. I think it's really pretty. So these all have rotations. And again, we can define these sort of centers of symmetry. So here I'm sort of defining centers of symmetry. There's lines here. The lines here don't actually mean all that much. I'm just kind of using them to highlight the points. But the centers of symmetry here, I'm denoting each of them by a regular polygon with the number of sides of the fold of the rotation. So like a triangle for the Isle of Man, a pentagon for Hong Kong, I guess some sort of cuspy thing for the twofold rotations. So this is how I'm going to denote these. And again, these do have fundamental domains. These are actually a little bit harder to define per se than the others, because I guess I could take sort of any curve along here. Here I'm just using straight lines because it's easy to see, but those do have like a fluidity to them. So here's, I guess, the fundamental domains I've picked. And to trace out the patterns for these, I'm going to do something a little bit different than sort of stamping them out. So I'm going to take this wedge, I'm going to like roll it up into an ice cream cone, and then I'm going to roll the ice cream cone. I'm going to put the cone of the ice cream cone at this point and roll it and roll it and roll it, and then I can use that to trace out this shape. So this works pretty easily for our sort of these sort of point symmetries here. But this is maybe not so obvious for 2D symmetries. So here's a pattern. These also have a bunch of rotations to them. So what rotations do you see? Rotation along the points where all the lines meet. So like here. So what order rotation do you see? Or 6. Perfect. Anything else? Yes. Pardon? Yes, center of the star. Right here. What order rotation do you see? 3. Are there any others that people see? Yes. Absolutely. That's the sneaky one. That's the hard one to see. So they're pointing out that there's a star here and a star here, and there's this little wiggly line connecting them. So the center of that here is a twofold symmetry. So these are the symmetries that we see. And so here I'll show you in the video how you can define a fundamental domain and how this is going to translate to sort of creating the pattern on the full surface. So here's our fundamental domains. We've got the 6-fold symmetry, 2 3-fold symmetries, and the central 2-fold symmetry here. And so they're going to roll the shape up, sort of joining lines together, and then they're going to inflate it like a samosa. And then they're going to take their samosa and roll the samosa around each of these cone points. So we've got 3 there, sorry, 6 there. I guess the 2 went really fast. And so this is how here's, I guess, where the 2 was. So that whole process of rolling out this samosa is enough to track the entirety of symmetries of this pattern on the plane. It's inflated because basically it doesn't need to technically be inflated, but it's saying that the 2 sides of that surface are different. So it's if it's sort of puffy like our ice cream cone was, you can kind of imagine the rolling out around those points a little bit more easily. But if it's flat, no one's going to really see obviously that this side of the surface and this side of the surface actually have different patterns on it. So it's more like a visual aid. So you don't actually have to do that. Yes. Yeah, I think you preempted my next slide. So here are the symmetries. So we're gonna define this symmetry group by the rotation. So it's a 6, a 3, and a 2. These ones don't have stars because they're not mirrors. So that's just to distinguish the counting. Okay, so as pointed out, there are translational symmetries as well. And I guess, you know, we're very used to thinking about translational symmetries and thinking about this. And so this is going to be for this group of people, the most obvious of all of the symmetries and how we sort of represent it in this sort of compact structure. So here's again a video. So, oh, by the way, all of the patterns from the attractor software are based on patterns like found in the ancient world in different places. So from I think like Egypt and a lot of Islamic art and things like that. So that's where all of these come from. So here's how we would do a translational symmetry. And as obvious to physicists, we say, well, this is just a torus. So I'm going to identify the orange side with the orange side, roll that up, the blue side with the blue side, roll that up. And then I sort of do the same process and sort of unwrap this structure around the plane, trying to get your anything with periodic boundary conditions to do this is not the easiest thing in the world. So that's how we do this. So absolutely translations fit into this. So there's one other symmetry that we have here. Actually, there's so there's one other type of symmetry that we have. So this is a glide symmetry. So the glide symmetry is sort of, it's like a translation, but also sort of, I guess, translated over at the same time. And so this one is made up of a slightly different kind of shape. So here's what our structure is. So I'm going to say, okay, so here's a blue edge and here's a blue edge, but here they don't meet up the way we think. So this is giving us a non-orientable surface. And so this is going to unroll one way, and then there's a mirror through it on its boundary, and it'll unroll the other way. So this is, so we can have sort of this type of structure. And these non-orientable surfaces we're going to call sort of cross caps. And so that's the other type of structure we can get. And so all of these sort of fundamental domains, these sort of objects that are equipped with the symmetry information, we call these orbifolds. So they're like manifolds, but they have boundaries and singular points that normal manifolds don't have. And we can use them to sort of try to understand a little bit about these structures. So I told you a little bit about the Euler characteristic before. So what we want to do for each of these structures, we can sort of build up sort of a catalog of what's going on to create each of these, like sort of the curvature of each of these orbifolds. So what we do is we start with this, start with a sphere. So we always start with a sphere, and that has Euler characteristic 2. So this is sort of our identity. We start here. And then to this sphere, we can perform all sorts of different operations to them. So we can add a handle to it. So a handle means we're taking -2 from our Euler characteristic. So here from our we add a handle to our sphere, so we get 0. So this is our torus. We showed earlier that has an Euler characteristic of 0. I can sort of do the glide symmetry, which is what we call a cross cap. I guess because it sort of looks like an X in the line version. So this is our cross cap. And to the Euler characteristic, we subtract 1. So this is sort of adding a boundary to our manifold, or to our orbifold, I should say. So mirrors, like a single mirror, is adding a puncture to our plane, or sorry, our sphere to get a plane. So to do that, we would subtract 1 from our orbifold. So we can also look at the sort of cone rotations and the mirror rotations that we have. And so these numbers A and star K, these are counting the number of like the order of the rotation point, order of the rotation at point A, and here is the order or the number of mirrors that intersect at point K. Yes.
So for the handle, here with the handle, is that 2 or 0? I think is the label or not?
Oh, the pink is the label. It has Euler characteristic 0 at the same time. This font is a capital O, but it makes it look like a 0. Yeah. So. Yeah. So I start with this, and then every modification I make, I add this number to it. So I start with a sphere and I take 2 away from it by adding a handle. So this has Euler characteristic 0.
Delta with a I see.
Yeah. So each of these features are sort of contributing that much to the Euler characteristic. Yes.
Do you why make the mirror?
Oh, so as that's actually a complicated one to see strictly in this way. This would be if there's a single mirror on it, it would be like say like the northern hemisphere of a sphere is mirrored to the bottom hemisphere of a sphere. So that's not something that's flat. So we would actually have to have two mirrors in it to create something that can tile the plane. And I'm gonna get to that in just a second. So that's a great question. So this doesn't obviously look like a mirror. Let me just quickly show how these go together, and then we'll work a couple examples. Yes.
So I'm a little confused about this sphere. I guess that what you're really doing is you're taking your group of rotations, right? That's your sphere, and then every time you quotient something out, you're getting these weird shapes, right? That's basically what's going on.
So the sphere here is not the sort of same sphere as the sort of group. So the group of rotations is like it's the group of rotations in the plane, and then we're quotienting that out and trying to take whatever is left over and make as close to a manifold as possible. And so we want to find out what the Euler characteristic of that thing that's left over is. And so we do that by taking a sphere and then starting to like poke holes and stuff in the sphere to try to create that orbifold. Yeah. So I'm just going to quickly show the cone point. So if we have like a six-fold rotation, we would have A would be 6, so we'd subtract 6 minus 1 divided by 6. So we'd subtract 5/6 of the 5/6 from our Euler characteristic. And then the same with mirrors. Here we have, 4 mirrors meeting at a point. So we would say K is equal to 4. So we would subtract, 4 minus 1 is 3 divided by 8. So this would be subtracting 3/8. So we'll do the examples of the sort of two ones that had like 6. So we can do these two as examples. So here we have okay. Sorry. Let me try that again. Okay, so we've got our star 4, star 4, and star 2. Okay, so what we would do to create this orbifold is we start out with, a sphere. That's okay, I've got an egg, but it's a topologically a sphere. So this has Euler characteristic equal to 2. And then what I want to do is I'm gonna sort of cut it open to make these mirrors. So I do the cuts to create, here's one mirror, here's my star 4. Then I'm gonna cut it again over here to get my star 4, and then those two meet again and get a star 2. So the Euler characteristic for each of these, what I would do is I'd say, so chi for each of those is equal to minus k minus 1 divided by 2k. And so we've got k equals 4. We just worked that out. So chi for star 4 is equal to minus 3/8. And then chi for star 2 is equal to what is that? That is equal to 2 minus 1 divided by 4. So minus 1/4. And so because when I first cut this open to start adding these mirrors to it, I had to place like an initial cut. That means I started not with my sphere, but my sphere that has the little cut in it. So I have to subtract off chi equals -1 from that. So I'm going to add all of these chi's together. So I have chi total is equal to 2 from the sphere, -1 from the cut, minus 3/8 from each of the 2 star 4s, and minus 1/4 from the star 2. And so I add these all together. So I have 2 minus 1 is 1, minus 3/4 is 1/4, minus 1/4 is 0. So this gives me an Euler characteristic of 0. And this is pretty interesting. And that's because my plane itself is flat. That is a flat surface that has Euler characteristic 0, because it's sort of like the lift of the torus. So what this is telling me is that if I want to have an orbifold that has that can tile a specific surface, then its Euler characteristic has to be equal to the Euler characteristic of that sort of topological surface. So if it's 0, it's a flat surface. If it's positive, it's a spherical surface. And if it's negative, it's hyperbolic. Yeah, so basically I've sort of cut the sphere open, and then I sort of take that opening and I make these sharp cusps in that opening. So it is the final thing is just that triangle.
Not sufficient.
So I guess that's probably true. This is, yeah, so I mean, so what I didn't say is that the symmetries I showed before are the only symmetries you can have in a plane. So were I to prove that rotations, reflections, glides, and translations were the only set of symmetries you can have in a plane, then it would be sufficient, but I didn't do that.
Have those symmetries plus Euler characteristic 0, then it tiles.
Yes. Yeah. So yeah, had I shown that those are all the symmetries you can have, that plus Euler characteristic 0 is sufficient. I didn't go through and show and prove that those are all everything, but yes.
That was just rotation symmetric and like threefold rotation symmetric. So it
Mhm.
was a cone. The only
Mhm.
symmetry was a cone. Then you would look at the Euler characteristic, and it would be like 3 minus 1 divided by 3, so 2/3, negative 2/3, and you subtract that from the sphere. So you get 2 minus 2/3. That's not good.
So yeah, so I guess thinking about point groups is a little bit different, because from that point of view, like we don't really have as much information about like the sort of boundary of the object. So these are sort of like these sort of more generally complete. Yeah. So that you can have multiple different things, because if you do have like the boundary of an object like a cone or a disk, like that can give you a non-integer value of things like Euler
But if
characteristic.
it's an infinite, right, then that
Infinities
cone
are
would-
weird. I don't
Okay.
in this case, I don't understand what topology plus infinity means. I imagine a mathematician who's thought about infinities would have a much better answer for you. So
So when you say that it has to add up to 0, this is like only if you have like a finite like situation that you yes.
So would you like to work through the example for the rotations as well? Okay, so let's work out the example with the rotation. So here we've got our 6-fold rotation, a 3-fold rotation, and a 2-fold rotation. So here we start out with our sphere. This one's a little less eggy. So we start out with chi equals 2. And then for each of the cone points, so I've got one cone that has a 6-fold rotation. I guess I'm gonna do one cone that has a 3-fold rotation, and then one cone that has a 2-fold rotation, and then we'll sort of join those up in the middle to create our sort of samosa structure. So the Euler characteristic for each of these is, so pi for rotation is a minus 1 divided by a. So we worked out before for the 6-fold rotation that was 5/6. For the 3-fold rotation, this is equal to, I guess 3 minus 1 is 2/3. And then for the 2-fold rotation, pi 2 is equal to 1/2. So our total, oh, sorry, these have minus signs in front of them, excuse me. So our total Euler characteristic is chi total is equal to 2 minus 5/6 minus 2/3 minus 1/2. And because I'm really bad at doing fractions in my head, I'm gonna do it, this is 4/6 and 3/6. So I've got 5 plus 4 is 9 plus 3 is 12. So that is 2 minus 12/6 equals 0. So pi total again equals 0. So basically we can sort of continue this counting for any of these orbifolds. And so it turns out that there's 17 planar symmetry groups that generate structure things like this, and these are called the wallpaper groups. And you might ask, well, why are there 17? And so So there are 17 wallpaper groups because we're looking for every case in which combinatorially we can combine a sphere plus whatever combination of these things where A and K are integers. We're looking for every way of combining those things such that you get 0 Euler characteristic. And so now this is just a pretty quick combinatorial problem. And it turns out we don't have to do all that much math to solve it, but it's something I'm not going to do for you, but I will show you what all the results are.
Just look at computer, sort of like just calculated constitution.
Yeah, you could do it with that. Like you could easily find like the largest integer for which this breaks down and then just test integers up to there, and it would be really fast because the largest one is 6.
Did people know about them before they had the computers, or?
Oh yeah, so people have known about this for a very long time. I think you were saying that the proofs that you've seen are people take like all sorts of symmetries and then start throwing things away. So I think this is a cleaner proof personally, but this is, you know, so people have known this for a very long time, but this is a newer, more I guess friendly approach to it, I'll say. So I guess, so this is, I'm going to show you stuff from, this is software called Attractor, not Attractor, sorry, this is software called iOrnament, and I'll show you a little demo when we're done with this. But basically, for rotations, I can add up like all combinations of things that have only rotations together, and that give me 0 Euler characteristics. So we showed that 632 does. Additionally, 442, 333, and 2222 do these. And so what this software attractor does is you sort of draw something in a square, and then it applies these symmetries to it. So here are what I get. So this is my 6-fold rotational symmetry. So I guess that's the point right here. There's 3-fold rotational symmetries here, and then this 2-fold rotational symmetry here. So this is my silly flowers version of what we saw with the much nicer set of swirly triangles. Similarly, we can have 442. So we've got a 4-fold rotation, a 4-fold rotation, and a 2-fold rotation. 333 has 3 centers of 3-fold rotational symmetry. And 2222 has 4 2-fold rotational symmetries. So I guess I can take this point and sort of rotate it into this point. Same with this. And then maybe not as obvious as this gets rotated around to this. So we can combine, let's see, oh, we can also do mirrors. So that's the other example we did. So we worked out star 442, but there's also star 632, star 333, and star 2222. And this is what they are. So there's a lot of mirror symmetry passing through this point. There's 3 mirrors over here, and then there's 2 mirrors on the side here. This one is the one we worked out together. There's 3 mirrors that join in 3 different places for this one, and then 4 mirrors that join like this. We can also combine rotations and mirrors together. So that gives us another set of 4 things. We have 4 star 2, 3 star 3, 2 2 star, and 2 star 2 2, which are, I guess, how you say these things is you put the rotations first, and then as soon as mirrors come up, you say star, and then add all the mirrors in a row after that. So these are kind of fun patterns. So I guess 4 star 2 has a 4-fold rotation and then 2 mirrors. So that's a very pretty pattern. I guess 3 star 3 is also a very nice pattern. So you've got this 3-fold rotation here, and that gets mirrored over to here and here and here and here and here. 2 2 star has 2 2-fold rotations and then a mirror. So there's again another mirror up here. So it's this sort of this strip along here. 2 star 2 2 has, I guess, 2 mirrors passing through here, another set of 2 mirrors passing through a different point over here, and then a rotation here. So there's all of these other sort of special things. You can have multiple cross caps. You get sort of 2 glide reflection or glide symmetries together. You can have a cross cap and a cone. sorry, the parenthesis is supposed to go after the cross cap, not after the cone. You can have non-intersecting mirrors. You can have a cross cap and a mirror. So that's the glide that we showed with the sort of G-shaped one, and then translations are the sort of torus. And so these are sort of slightly different versions. So the two glides is probably the hardest visually to spot if you're looking for symmetries in the wild. So here we've got like one glide reflection in this direction. So we've got a sort of translation and rotation. There's also a glide symmetry in this direction. So we have like a translation and a reflection through there. Two mirrors gives us this structure. Here we have two rotations in a glide. This is also kind of hard to spot. Actually, anything with glides is pretty challenging to spot, to be honest. Here we've got one glide this way and then a mirror passing through the diagonal through the center of the flower. And then we've got just our standard translations over here. So give me a second to switch up my setup and I can show you eye ornament. Oh, there we go. Thank you. I guess I just stretched it too far. Thanks. Okay, so this is eye ornament. Honestly, I don't remember if it's free or paid software, but I think it exists. If it is paid, it's pretty cheap. So I guess this might be a fun thing for those of you who are in the t-shirt design business. So basically what you do, so okay, so I drew this flower before, so I can say, no, I don't want to do that. Let me create a new drawing. So let me do, I don't know, don't remember exactly what the Colorado flag looks like, but I could try drawing something, I don't know, or Boulder might have a, let's do this translation first. Hold on, where is my, so I can draw maybe a C, I don't know, I think this is my attempt at very poorly remembering what Colorado's flag looks like. So, oh, okay, cool. Okay, I got the colors right, just the order of the colors wrong. Okay, so here's my poor attempt at Colorado flag. Okay, so we've got our Colorado flag, and so here are the seven. So now I've got my drawing. I can apply all of these different groups. So here's a glide symmetry. Here's two mirrors. Here's a glide. What is this? This is the glide and the mirror that we saw. I think this is a two glides one. These are always the ones that are hard to pick out. I think these are a bunch of, I guess these are, what is this? 442, I think. So you can play around with this. Yeah, you got to be a little careful with star 442 because you cannot not get swastikas. It's you just got to be careful with that one. I guess there's more or sorry, 442, not star 442, the rotational one. So here, this one has reflections. Here's, this is, I think, what makes brick patterns. Here's threefold. This is, I think, 333, sorry, yeah, 333. This is, I think, 3 star 3. I think this is one of the, oh gosh, this is 3. This might be 3 star 3 actually. This is the 632 and then star 632. So anyway, so here's this is maybe a fun tool for those of you who are in the t-shirt making business. So the thing about these orbifolds that's actually pretty fun, so, oh, we can also do like point group symmetries here. So this is rotations about point groups. Anyway, so this is kind of a fun thing to play with. So the thing about orbifolds that's quite nice is that what I said for planar symmetries is something that also holds for symmetries of other surfaces. So one of the things we can look at back here are, we've got some sports balls for all of you sports ball fans out there. We've got, I guess, a basketball and a soccer ball. So these all have sort of interesting symmetries, especially if you ignore the writing on them. So the basketball clearly has a mirror symmetry through here, also has a mirror symmetry through here. So that's going to be one thing it has. It also, does it also have anything else? It might have something else. These are not the easiest things to spot always. The soccer ball is quite interesting. So it has almost cubic symmetry, but it has some chirality to it. So if you look at this point here, so this is something that, you know, looks like it would be the corner of a cube. You can trace out those sort of 6 patches, but the orientation of the 6 patches wraps around. So this would be a center of threefold rotation. We could find, I guess, this would be a mirror, this would be another mirror. So it looks like we'd have a center of threefold rotation and 2 mirrors. So we can sort of do the same thing for spherical symmetries. And so these are, whoops, hold on. What happened to the rest of my presentation? Oh, wow, that got, something got mixed up. So here are, basically we can do that combinatorics again, and we get we get anything that has Euler characteristic of 2 gives, I guess, these sort of spherical orbifolds. And so here are all of the symmetries. So a lot of them have, I guess, infinite families of symmetry. So I think this is sort of what you were pointing out, is that in these sort of point symmetries, you can have sort of arbitrary angle as long as it's like 2 pi divided by any integer. And so that's the same thing here. So we've got these things that have like 8 rotations about the top point and the bottom point. Or here there's 4 rotations about or there's 4 mirrors over here. So these are infinite families. So you can have 8 mirrors or 256 mirrors or whatever you want. So I think everything over here has infinite families. And then the 7 over here are ones that are sort of combinatorially fixed, because those are more fixed things. So we're looking for a positive Euler characteristic here. We can do the same thing for a hyperbolic plane. And so we'll, I guess, as an exercise, we can look at, this is circle limit 4, or angels and demons. This is one of the Escher lithographs, probably the most well-known of the sort of hyperbolic ones. So the story behind this, I guess I'll tell while I'm trying to get everything set up again, is so Escher was really interested in the concept of what is infinity, and how do you see infinity? So in Euclidean space, or flat space, I should say, not Euclidean, we're used to thinking about perspective drawing and things like that. We all sort of draw vanishing points. And so the idea of infinity is this point that's infinitely far away and infinitely small. So how do you draw that? What is a way of drawing that? And so he learned about the hyperbolic plane. And this particular model of the hyperbolic plane is called the Poincare disk model. This is a specific mapping into the unit disk that is conformal. There's another mapping into the unit disk where geodesics are straight lines. That is not a conformal map. This one has geodesics as arcs of circles that make right angles with the boundary. So if I'm looking at sort of straight lines in this, I might trace a line. Hold on, where would I would trace a line along here. And so that curve, I guess I should do this so everyone can see it. So a curve that, I guess, follows along a line like this, where it intersects the boundary as a right angle, and as the arc of a circle would be what's called a straight line in this model. And so the idea of this model is that there's this central motif. There's these 3 angels and 3 demons, and they are sort of interlocking around. And then at each of their wingtips, there are, I guess, 4 copies of the same angels and demons. And if this was really hyperbolic space, this would be roughly. So remember, hyperbolic metrics are characterized by saddle-shaped surfaces. So this plane would be sort of a saddle shape everywhere. And in fact, it's a theorem that you cannot embed the entire hyperbolic plane in R3. There's too much of it to fit without intersecting itself. So this is one way of trying to view the whole thing. And so Escher was interested in this way of viewing infinity. And so this is he talked with the mathematician Donald Coxeter, and they sort of talked about this model. And so the thing about this model is that infinity for the entirety of the hyperbolic plane is now mapped to the edge of this unit sphere, or sorry, unit disk. So that's this model. And so what we want to think about is that this demon here and this demon here, they should be the same demon. If I was looking at a line of reflection, obviously these central figures have, you know, reflection symmetry through different points. But if I look at this demon out here, so the straight line is tracing like through his body, through this angel, through the next demon, blah, 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 and down. So that's my geodesic. I can have a reflection about that geodesic. Let me show you. It's easier to point on the big thing, but let me show you on the small thing with the giant pointer. So if I look at this demon here, there's a mirror that goes through the center of his body, through the center of the angel, the next demon, the next angel, so on infinitely far. And I can trace it the other way. So it goes through the center here, through here, through here, through here. And that's the arc of a circle that intersects the boundary and right angle. So that's a geodesic. So I can have a mirror in my surface, or my surface, in my tiling that way. So so I showed you, I guess, the three mirrors about the center. We should also think of mirrors that go along here. And here, another one would go along here. And so on and so forth. So these are all mirrors. And I noticed that this one has a threefold intersection, so I have a star 3 there. This is an equivalent point. This is an equivalent symmetry point. This also has a threefold mirror. So, oops. Hold on, let me write these in because I think these are not builds. So we've got threefold mirrors. And then we've got some rotations. So we've got rotations about the tips of the wing. So every place we have a wingtip, we've got rotation, rotation, rotation. We've got, I guess, this angel demon pair gets mapped to this angel demon pair, gets mapped to this angel demon pair, gets mapped to this angel demon pair. So we've got these rotations here. So we can work on sort of building orbifolds out of that. So in this particular case, we have 4 star 3. So we've got one rotation center that has 4 and then 3 mirrors that intersect. So remember we had, I guess 4 star 2 was one of the flat ones. So here we've subtracted off an extra bit for the extra mirror. So any combination of these orbifolds that has negative Euler characteristic can be something that maps onto a symmetry of the hyperbolic plane. And I guess one thing I will say is that that's one sort of obvious set of symmetries. The sneaky thing about this painting that's not so obvious is that these central figures here, the demons in the center, are facing towards you. These demons and angels here are facing away from you. So if I were to count that in, that's a whole other symmetry. So I will leave that as an exercise to you to see if you can figure out how to take into account the symmetry of having demons facing away from you with demons facing towards you as well. So here are several other Escher lithographs, and these all have different symmetries here. So the one with the birds up top makes it pretty clear what I was talking about these sort of mirror lines being the right angles that intersect with the plane. So you can see there's a mirror line through the center of this bird or fish, I guess. I'm not quite sure with Escher, they're one or the other, or both. And here's another line that passes straight through the center of these fish. So this is another arc that intersects the boundary at right angles. So here's a point of reflection. These are quite interesting since the pattern is, it's, I guess, it's regular, but has multiple things going on. So here's a place where 4 fishes have intersecting fins, and here's a place where 3 fishes have intersecting fins. So this is a little bit more subtle. Here again, you can see lots of places where you have reflection symmetries going through different curved paths here. So orbifolds are something that can be extended beyond these sort of 2D surfaces. These are something that work for 3D structures as well. And this is not quite as well known. So there's at least one paper I know of that classifies the, was it 236 or whatnot, space groups in 3D as three-dimensional orbifolds. I'm not sure if it's 236. It's like 230 something, but I don't remember how many exactly there are. And as with the idea of geometrization, in 3 dimensions, we can also start creating sort of uniform structures on space. So we are used to thinking of our space as being flat locally. So I can have, my metric is just a vector space. I have, regular cross products, dot products, all of those things work in my standard class mech version of space. But imagine you're near a black hole or something like that. You don't have necessarily the same metric. Your metric is going to be curved, and in that case, its curvature is spherical. It's not uniformly spherical because very, very far away from the black hole, it approaches flat, and at the sort of event horizon, you end up with a sort of singular point. So that's not a uniform spherical metric, but you can construct a space that is uniformly spherical, and that's the 3 sphere. So my necklace is a thing from the 3 sphere. I can tell you about that later if you're interested. And so it turns out that you can also do 3-dimensional hyperbolic space equivalently. But 3 dimensions are weird. It turns out that unlike just the standard spherical, flat, hyperbolic metrics, there's 8 possible uniform structures you can have. And so this geometrization conjecture is only solved fairly recently, I think in the 90s, or maybe early 2000s. And so I guess there's the standard 3, there's 2 more that make sense. So like taking a 2-dimensional spherical space and one direction is Euclidean, or a 2-dimensional hyperbolic space and one dimension is Euclidean. So those 2 make sense. And then there's just 3 weird ones. And so we wanted to understand these. So we made a sort of virtual reality sort of tour of what it would be like to live in these spaces. And so here's some screenshots and videos of that I'll end on. So these are all Euclidean. So we can see different, I guess these are all cubic Euclidean symmetries. You can sort of see that idea of the vanishing point we were talking about before. So infinity just goes away as far as we're concerned. But some of these are pretty strange. So this is again Euclidean space, and you can sort of see how this is what it would be like to live in a 3-dimensional torus. So if your actual torus has this sphere and this light source orbiting it, you can see multiple copies of it, because in the torus, the light goes out one side and comes around the back, like asteroids, which is well before my time, but retro games are super popular now. So you might have heard of that from video games. This is a spherical space. And this is another strange one, because when you're in spherical space, if you see in front of you, that goes around like in a 2D sphere. If you start looking one direction, it goes all the way around a great circle, it comes back. So here, everywhere you look, you're staring at the back of your head. So that's a pretty funny space. This is a video of that, so you can kind of see things like passing through infinity occasionally. So you get this like everything's there. So that's like the South Pole to your head is the North Pole. this is hyperbolic space. And here you can see some different sort of symmetries. This one is based on cubes, and here there are 6 cubes around an edge. This one is based on dodecahedra, and I think there are 3 dodecahedra around each edge. And here's a video of that. If you are interested in the other wacky spaces, please visit free-dimensional.space, and you can, if you've got a good enough GPU, you can fly through them, and if you've got a VR headset, you can go inside them. They don't make you as sick as you think they should, because one thing about differential geometry that we didn't really talk about is that on a small enough scale, everything seems Euclidean. So moving your head around, everything locally tracks. It's just stuff that's far away that looks weird. So with that, thank you for your attention. And I guess it's coffee break and photo time.
All the weird symmetry. You get something like a flux here. Like, does that even make sense in this case? Like, if I had
Yeah.
An electron jumping through a crystal with these like orbital symmetries, is it obvious that there's a flux theorem associated to that?
I don't know how obvious I would say that is. I mean, I guess, I guess you'd have to say a little bit more about what you define as like plane waves and things like that. But I sort of don't necessarily see why there wouldn't be some analog of something like this. I will say that these orbifolds are actually what's under the hood of all of our knitting simulations. So we just actually take like a very small crossing and then look at how it connects up to itself in weird ways. So it's a nice way of looking at periodic structures in an even smaller way. So I think there's probably something similar, but I'd maybe be like a little bit cautious about the things that have like rotations or mirrors. Like mirrors would probably break a lot of those ideas, because that's a specific type of discrete symmetry that tends to break most physics. Rotations, you might be able to write an e to the I something that's good enough for that. And glides would be a little bit interesting, because you'd have to define your waves on a non-orientable surface. I guess you're probably the most familiar with that than anyone else in this room. But I imagine that things that are not mirrors, you can have some extension to, and mirrors, I don't know. Mirrors are weird.